Welcome to the lecture series on the control system. So, this is the first online lecture on the control system. In this lecture, the brief introduction of control system is given, and then its type of the system, historical development of the control system, classification of the control system, open loop system, closed loop system, and their comparison. So first of all, I'm going to talk about the system. So what is system? So one can define in a very simple language. The system is a coordinated unit of various components which performs a specific job. And one of the common example is any academic institute or university in which the specific job is to graduate students at a UG level, PG level, and doctorate level. Having a number of department means there are various components, and that makes a common effort maintaining a norms and standards produces every year graduates, undergraduates, and postgraduates. Similarly, other examples are like transportation system, solar system, telephone system, weapon system, ecological system, and space systems. A lot more systems exist you can observe in your daily life. So basically, the systems are two types. One is a physical system, another one is a non-physical system. And physical system can be further classified as a electrical system, mechanical system, chemical system, and many more. So, in which the specific job is related to electrical output, mechanical output, and chemical processes, and then their output. Similarly, many more systems exist. While in a non-physical systems, as I have given example of academic institutions, so there is a institutional system that may be any type of the institution, economical system, and many more. Now coming to the control system. What is control system? So like a system, we can here see that control system can be defined as a combination of a various subsystems which control a set of quantity with respect to a reference quantity or input variable. The quantity that is controlled called controlled variable, and the quantity which is input or with respect to which, that is called a reference variable or reference value. So basically in a control system, we control a set of parameter or quantity with respect to some reference to get the specified output. Examples, specific example of control system in electrical engineering and electronics engineering and many more. The position of shaft of a motor, speed control of the speed of the rotor, control of the position of rotor, control of the plane, automobile, lots of examples you can observe in your daily life. So to design To have a control system, there are basically three steps. First one is modeling, second one is analysis, third one is design. So any system we have to design, we have to model it, then analyze it according to our requirement. If analysis is okay, then we will move towards the design, and if design is okay, then we will move towards the prototype. If any step is not fulfilling the required specification or desired output, then we will move back to the last step or first step, that is a modeling. So there are many approaches of the modeling. So basically it is classified in two ways. First one is conventional approach, second one is a modern approach. So in a conventional approach, one can adopt either differential equation theory or transfer function theory. In modern approach, state variable and many more. So this is the first step for obtaining a control system. Means either we can use the conventional approach or modern approach depending upon our choice and availability and skill we have. Next one is analysis. So analysis can be further classified in a two-way, that is a conventional approach and modern approach. The conventional approach, basically there are two type of the analysis is done. One is time domain analysis, second one is frequency domain analysis. While in modern approach, state variable and many more. Now, third step is design. So design can also be done by two ways. First one is conventional approach, second one is modern approach. So conventional approach, board plot method, root locus method, Nicholas chart method, these are the conventional approach. While modern approach is pole placement, optimal theory and robust control theory. So these are the various approaches. So to obtain any system or any control system, so we have to go through the three basic steps. First one is modeling, second one is analyzing, third one is designing. So if modeling is okay, then we will we will analyze that model, that mathematical equation, and if analysis is okay, then we move towards the design. If not okay, then we will go back to the modeling and we will rethink and remodel, and then we will go to the next step, means analysis. Analysis is done. If it is okay, then we will move to the design, and if design is okay, then we will move towards the prototype modeling. If prototype modeling is working, then we will move to the uh, 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 pilot project level. So is this is the way we can design any system, especially the control system. Now, general application of control systems in our homes, cars, industries, scientific laboratories, and these have a vast impact on the engineering, aeronautics, economics, medicine, and others. So, while specific application of control system one can see in a flight control system, robotics, chemical process, industrial process, and automotive. These are the specific application of control system. So, like other system, control system have a some basic component. Here, the basic components are First one is a plant, second one is controlled variable, third one is expected value, fourth one is a controller, fifth one is activator, sixth one is a sensor, and finally there may be disturbance in the system, so disturbance can also be considered. So what is a plant? Basically, plant is any physical system that is to be controlled by a controller. So it is a heart of the system that gives the output. If any there is a parameter variation, then we have to put the controller. So next one is control variable. So the variable controlled by a controller considering as a system output. So that is a controlled variable. The variable which is controlled. Expected value means desired value of the controlled variable based on the specification or on requirement with respect to reference used. And controller and unit that can compute the required control signals. So basically a controller that gives a control signal. And next is activator. What is activator? Basically, it is a mechanical device which converts energy into some kind of motion. Usually, energy may be air energy, electricity, or any liquid. And then sensor. What is a sensor? A device that measures a physical quantity and converts it into a signal, and which can be read by an observer through an instrument. So this is a sensor. And finally, there may be disturbance to the system. So that is unexpected factor disturbing the normal functional relation between the controlling and controlled parameter varies. So these are the 7 basic component of control system. Now block diagram and transformation. So any system if represented by a blocks, that is called a block diagram, or a pictorial representation of a system by block that gives the relation between input and output. So the control system receives input signal from other element or any input device and provides the output signal as desired. So this is a block diagram of open loop control system in which you can see that a input, an output and system may consist of a number of elements. So this is the block diagram of open loop control system. Now block diagram of a closed loop system in which you can see that a feedback signal is passed to the summer through a sensor. That feedback signal is sensed by a sensor and that is passed to the summer, and this summer compares the feedback signal with the expected value and generates the error signal. Then error signal is passed to the controller. Controller pass, passes a signal to activator. Activator generates a controlling signal that is passed to the plant, and finally we get the output. If output is as the accepted value, then it will keep on working as a stable mode within the tolerance band. If not, then this feedback signal will be again processed and error is minimized and keeps on working. Now the transfer function. So any control systems transfer function can be defined basically for the linear control system can be defined as a Laplace transform of the output to the Laplace transform of the input at initial condition 0. So here it is a output. This output Laplace transform is obtained, then input Laplace transform obtained. So Laplace transform of output to the Laplace transform of input is defined as the transfer function. Now, open loop control system. What is open loop control system? So in this, there is a no effect on the control action of the output. So output have no effect on the control action. So basically, the signal is passed to signal is given to the input and then to input and input of the controller and controller generates a control signal that is passed to the plant and plant gives the output. So this is the simple block diagram of the open loop system having the output, plant, control signal, controller and input. So this is the open loop system block diagram. The Here you can see the output is neither measured nor feedback for comparison with the inputs. So for each reference input, there correspond a fixed operating condition. Basically, in this case, accuracy means depends on the calibration of the system. So output will be accurate as the system is properly calibrated, as the system parameter does not vary with the time, so that will give the accurate output. Means accuracy will be high. While in presence of the noise or disturbance, so there might be chances that its performance may deteriorate. So performance will not be at desired. Features of the open loop system, you can see it is a very simple and maintenance is very easy. Simple and very easy. Simple and very easy. Less expensive, no stability problem, recalibration is necessary from time to time, sensitive to disturbance and so less accurate. So there are features they, which you can see that very simple, ease of maintenance, less expensive, no stability problem, but it is a sensitive to the disturbances and recalibration is required time to time. When we should use the open loop system? When we don't know exact relationship between input and output. We don't know exact relationship between input and output. There is a neither internal or external disturbance. So we know that there will not be any disturbance, then we can choose the open loop system. And another factor that is responsible for selection of open loop system, when the measuring the output precisely is very hard or economically not feasible. So then we will choose the open loop system. So open loop system uh, can be chosen when the exact relationship between the input and output is not known, internal and external disturbance are not present, and measuring the output is not economically feasible, then we will choose the open loop control system. There are lots of example of open loop control systems. One can see ceiling fan, speed control of motor, automatic washing machine, electric valve, hand dryer, time-based bread toaster, TV remote control, clothes dryer. So there are lots of example of control system. You can see this. Now to the uh, closed loop system. S- It is also referred as a feedback control system because the output is passed at a summer for comparison at the input side. So in this case, a signal from the output is taken and moved, uh, given to the summer at the input side, and comparison takes place. So basically, the comparison of actual output with references takes place, and it's basically designed to perform based on the error. And this is the foremost design point. Foremost feedback is a foremost design point, and it is really very influential and powerful. Examples of uh, closed loop system. Now we can see our AI based air conditioner that continuously measures the room temperature, that desired temperature when it's obtained, then its compressor go in the sleep mode. So this way, air conditioner maintains the room temperature at a specified value. Similarly, automatic electric iron servo voltage stabilizer in our refrigerator that maintains the voltage within the specified range, water level controller, and speed regulation of motor through a tachometer or current sensor, through a regulator or current sensor. So these are the various examples of closed loop system. And one can see lots of advantages of closed loop system, and there are also drawbacks of closed loop system. Advantage, you can see, reduces the disturbance effects because it works on the reduction of the error between the output and input. So if there is a noise or disturbance, that it takes care of these disturbances, and it is made such that it is insensitive to variation. If there is any parameter in the input or parameter variation of the plant, so that plant keeps on performing even though there is a change in the uh, parameter, because that is designed in a such a way within a tolerance range, its performance is okay. Normally, it stabilizes the unstable system, and there is a well-defined relationship between output and references. Drawbacks: there is a if it is not properly designed, then it may cause instability, and couple noise from the sensors into dynamics of the if sensor generates a noise, then that can also be harmful. And but the complexity of overall system increases. Complexity of the overall system increases. So this is the drawback of the system, closed loop system. So now we are in a position to compare the open loop system and closed loop system. So one can now observe that open loop system very simple structure, low cost, while closed loop system, as you have seen, that is a complex and high cost. Open loop system is easy to regulate, but it is selecting parameter is critical. So because it may cause stability problem. So open loop system is low accuracy and resistance to disturbance. If input varies, then accuracy of the system get affected. While closed loop system, you can see ability to correct error, high accuracy, resistance to disturbance. Complex structure and selection of parameter is critical. Now moving towards the classification of control system. Basically, the control system can be classified according to the structure, according to the reference input, according to the system characteristic, according to the signal form, and according to the parameters. So first is according to the structure. As we have studied, the structure may be open loop system, closed loop system, or composite system, that is made of open loop system and closed loop system. And while according to the reference input may be constant, and that may be variable, or you have to track the input or program input that is already programmed. So here reference input, you can see it is a constant. The controller works to keep the output around the constant value, like a temperature, pressure, or level. While servo or tracking input are varying, the input may be unknown or varying. The controller tracks the varying references, that is automatic navigation in our cars, or you can see that uh, GPS in our mobile phone for tracking the path, and satellite tracking antenna. And third one is programmed input, means input changes according to the program that has been already done. Controller works according to the predefined command. It is numerical control machine. Now, third classification you can see according to the system characteristics. So you can see linear control system, it can be classified, and non-linear control system. So in a linear control system, that follows the superposition law and homogeneity. So that is called linear control system, while in a non-linear system that does not follow the superposition theorem and homogeneity theorem. So the system based on the characteristics can be classified as a nonlinear control system and linear control system. So basically, this control system series will be focusing on the linear control system. Now, fourth way to classify the control system is according to the signal form. Signal may be continuous control signal and controls. Uh, discrete control signals. Okay, this is a continuous control signal, and one may be discrete. So, in a continuous signals are function of continuous time variable t, while in a discrete control system, signals are in the form of either a pulse of train or digital code or digital control system. So this is the fourth classification, and that is based on the continuous control system and discrete control system. Now fifth one is according to the parameters. This is important. Time invariant system and time varying system. So in this, what is time invariant system? You can see the parameter of control system are stationary with respect to the time. Stationary with respect to the time. While time varying system, the system parameter varies with the time. So example of this guided missile control system, time varying masses results in time varying parameter of control system. These are the five classification of the control system. Now why we need control system? Because we need the stable output, we need the response quickly, we need the output as accurate as possible. So stability, what is stability? Ability of system to recover equilibrium, means as soon as it should be stable and output should be as per desired value. And while quickness is time of response, so during duration of transient process before control system reaches to equilibrium. So here how quickly the transients die out, that is the quickness, time of response of the for the output. And accuracy, so what is accuracy? Basically refers to the size of steady state error when the transient die outs. If the transient die outs, then what is the value of the output, and if it is the desired value or not, or there is variation. That variation, if it is within the tolerance range, then it is okay. So basically, one can see steady state error is equal to desired output minus actual output. That may be higher or lower. Now, before completing this introduction to the control system, we we must also know the historical development of automatic control system, or basically the control system that has been developed to the automatic level. So first example of the automatic control system is the flywheel governor system for control of the speed of steam engine by the James Watt in 1770. So James Watt made a flywheel governor to control or regulate the steam in his engine. Then after 100 years, Maxwell analyzed the dynamics of flywheel governor system. While during the First World War, that is between July 1914 to November 1918, as you can see in during the war there is a need of ammunition and heavy cannons, missiles, guns. So in that case, for a quick response or quickly positioning uh, ammunition, so we need a precise system that can position ammunition that to be heavy masses. So in this period, there is a there was a need to work on this. So during the First World War, lots of work has been done in the field of control system by the various countries. In 1920, Minorowski performed a classical work on an automatic steering of ship's positionings of gun on shipboards. And then in the year 1934, Huygens developed a general theory for servo mechanism. And in the year 1940, lots of work has been done for mathematical and analytical method for development of a control system. And during this year, the control system was established as the branch of engineering. So in the year 1914, the control system has been developed as a specialized branch of the engineering. And during World War II, again, lots of work has been done in the field of control engineering because of necessary to design and construct automatic airplane pilots, gun positioning systems, radar tracking systems, and other military equipment. So during again the lots of work has been done in the Second World War during 1939 to 1945, and in 1955 there has been tremendous growth in the field of control engineering, and moreover in the 1940 Bode developed a diagram in a frequency domain for design analysis, and then Evans developed a root locus method for design and analysis, and in the late 50s optimal control system has been designed in some meaningful systems, and finally with the invention of digital computers, uh, lots of uh, conveniences, convenience has been developed to analyze a complex time domain problem, and that leads to development of modern control theory using the state variables. While in between 1960 to 1980, both deterministic and stochastic system as well as adaptive control system has been fully investigated, and from 1980 to present a modern control theory centered around the robust control has been developed. So this way, this is the brief introduction of the control system. Thank you very much. So we will see in the next lecture on the feedback control system.